Let's take a closer look at backpropagation, one of the core algorithms in deep learning. In this video, we'll focus on the fundamental theory of backpropagation. This slide shows a typical artificial neural network. In the diagram, each circle represents a single perceptron, which is usually called a node. Each node takes an input value x, multiplies it by a weight omega, adds a bias, and then applies an activation function to produce an output. For more details, you can check out the perceptron video. In a neural network, the output is compared to the actual value to calculate the error. To reduce this error, the weights and biases are updated. In simple terms, the core of training a deep learning model is finding the weights and biases that minimize the error. The process of updating weights and biases happens through a method called backpropagation. As shown in this slide, the error between the actual value and the predicted value is passed backward from the output layer to the input layer. Along the way, the weights and biases are updated. This process is called backpropagation and is a key algorithm that played an important role in the advancement of deep learning. Now, let's take a closer look at backpropagation. Suppose we have inputs x1 and x2, and the error at the output y is 0.6. This error is distributed back to each input based on their contribution. If x1 has a bigger influence on the output y, a larger portion of the error is passed to x1. On the other hand, if x2 has less impact, it will receive a smaller portion of the error. This contribution is measured by the rate of change of the output y with respect to each input x, which can be calculated using derivatives. For example, if the derivative of y with respect to x is 2, it means that when the input x changes by 1, the output y changes by 2. Using derivatives, we can quantitatively measure how much the input x affects the output y. This helps us understand how much each input contributes to the error. In the backpropagation process, the impact of each input on the output is calculated using the derivative of the output error, and the weights and biases are updated accordingly, reducing the error. As explained in the previous slide, the weights and biases of an AI model are updated by taking the derivative of the cost function. This process is repeated based on the following formula until the values converge to their optimal state. In simple terms, we calculate the partial derivative of the cost function, multiply it by the learning rate, and subtract it from the current weight to get the new weight. By repeating this process, the partial derivative becomes closer to 0, meaning the weights stop changing and eventually settle at fixed values. The formula below shows how a weight, omega, is updated by taking the partial derivative of the cost function with respect to omega. So, before diving into backpropagation, let's first take a closer look at partial derivatives. Partial derivative is the derivative of a multivariable function with respect to one variable, while keeping the other variables constant. When we do a partial derivative, we treat all the other variables as constants, and only focus on the one variable we're interested in. For example, if the formula is y equals omega x plus b, and x is the only variable, when we take the derivative with respect to x, the result will be omega. Now, let's consider a function z with two variables, x and y. If we take the partial derivative of z with respect to x, we treat y as a constant, and the result will be 2x plus y. Similarly, if we take the partial derivative of z with respect to y, we treat x as a constant, and the result will be 2y plus x. Next, let's learn about the chain rule, which plays a very important role in backpropagation. Imagine we have two functions, f and g. The function g is defined as the product of two inputs, omega and x. The second function, f, is defined as the sum of the already defined function g and a constant b. As mentioned in the previous slide, in the backpropagation process, we calculate the effect of each input on the result by taking partial derivatives, based on the error calculated at the output layer. First, if we calculate how g affects f by taking the partial derivative, the result will be 1. Similarly, if we calculate how b affects f by taking the partial derivative, the result will also be 1. Now let's calculate how omega and x affect the function f. However, since f does not directly include omega and x, it's not easy to calculate their partial derivatives directly. This is where the chain rule comes in handy. Chain rule is a fundamental concept in calculus used to compute the derivative of a composite function. A composite function is a combination of multiple functions, like f g x. In chain rule, we find the derivative of each individual function and then multiply them to get the overall derivative. In simple terms, the chain rule helps us calculate the impact of each value, even when they are not directly connected, by working through the intermediate functions. As shown in this slide, if we have a function z equals f of g of x, to find the derivative of z with respect to x, we multiply the derivative of z with respect to g and the derivative of g with respect to x. For example, let's suppose z is e to the power of g of x, and g of x equals 3 times x squared. The derivative of z with respect to x involves multiplying the derivative of z with respect to g by the derivative of g with respect to x. So, the derivative of z with respect to g is e to the power of g of x, and the derivative of g with respect to x is 6 times x. The final result is the product of these two values. Let's apply the chain rule to the example from the previous slide. We were able to easily calculate the partial derivatives of function f with respect to g and b, but f does not directly include omega and x, so we cannot directly differentiate with respect to them. However, by using the chain rule, we can differentiate f with respect to omega. In other words, to differentiate f with respect to omega, we take the derivative of f with respect to g, and then multiply it by the derivative of g with respect to omega. The derivative of f with respect to g is 1, and the derivative of g with respect to omega is x. When we multiply these values, the result is x. Similarly, differentiating f with respect to x is the same as multiplying the derivative of f with respect to g by the derivative of g with respect to x. The derivative of f with respect to g is 1, and the derivative of g with respect to x is omega. When we multiply these two values, the result is omega. In other words, the chain rule allows us to calculate the impact of each value on the result, even when they are not directly connected, by working through the intermediate functions along the connected path. This is why, even when a neural network is deep, we can efficiently calculate how each input affects the result, which makes updating the weights more efficient. Finally, let's summarize the process of updating the weights. First, we perform a forward propagation using the randomly initialized weights, calculate the output, and then compute the error. Next, we use backpropagation, starting from the output layer, and apply the chain rule to calculate the partial derivatives of the error with respect to each weight. Using these values, the weights are updated. Then we use the updated weights to perform another forward propagation and recalculate the error. This process is repeated, adjusting the weights in the direction that reduces the error. In the next video, we will go through the process of updating the weights through backpropagation, using an example to calculate it.